Hi everyone, welcome to quarter 4 of your senior year. We are starting with electricity. For your assignments this week, we are starting something new. I'm going to have two due dates during the week. The first will come after the first set of assignments when I see people Monday or Tuesday, and then the second due date will come Sunday night with your second set of assignments when I see you Thursday and Friday. So what we have going on this week, we are going to start with a quarter 4 info. You click through it, answer the questions. It's just getting some of the most basic stuff of what is going to happen during quarter 4. That will get you 3 points when you hit submit. From there, we're going to do the electricity notes right now, and through that, you'll be ready to complete the electricity problems. That will get you 5 points. Those will both be due by Wednesday night before you go to bed. I will wake up Thursday morning. I will put points in for those. You will have done these, so you'll understand electricity, and you will be ready to come back on Thursday or Friday in which to do the lab on electricity. The 2 assignments for the end of the week, the second part of the week, the electricity lab with the crossword puzzle, I will put the data in this video right here, so you'll just have to skip to the very end of it if you don't do it all at one time. That will get you 6 points, and then finally, just like on previous weeks, there will be an end of week 1 electricity check for you to go through. It's not math, it's kind of the basics, getting to know the different variables, what they're measured in, the units, and so forth. And that will get you 5 points, 1 attempt on that. All right, we are ready to get started. Let's learn about electricity. All right, so what I have here, this chart will be your lifeline for the first couple of weeks. The variable, that is going to be the letter that it will be in an equation. Here is the definition, then the unit it is measured in, and finally that unit will have an abbreviation. You don't have to write out amps or ohms every single time. It will have the abbreviation that we use, like meters is just an M. All right, electricity. In order to have electricity, you have to have a current. Current is strange. It is not a C, it is an I. And what current is it's the movement of electrons, those negatively charged particles, flowing through wires, and you have a current. Okay, we measure current in amps, which is abbreviated with a capital A. When the current meets an appliance or a light bulb or something that slows it down, it is said to meet resistance. Resistance, it is an R for the variable that you see in the equation. It is the opposition, that means it slows it down, to the movement of current. So it's what slows down the current that's flowing through the wires. It is measured in ohms, which is this little upside down horseshoe. It is the Greek letter omega. From there, we have this little guy here. We call it voltage, but it is also known as potential difference. That's kind of, you'll see different books and different places will call it one or the other, but it means the same thing. This is abbreviated delta V. That is how you'll see it in an equation, triangle V. And it's the rate at which energy is drawn from a source of electricity. It's what pushes the current through the wires. When you plug something in, you are getting a voltage for that object, and that is what pushes that electricity. It's what gets those molecules moving and causes them to start flowing. It is measured in volts. That's great. It's voltage, it's measured in volts, and it's abbreviated with a capital V. Just to kind of give you an analogy so that you can kind of think this, if you think of this in terms of a hose, think of the water being the electricity or the current that's flowing through. So when you're thinking of a hose, you go on to wash your car, you turn it on. The water flowing would be like the current. That would be the electrons flowing through that water going through the hose. Okay, resistance, when that hose gets kinked, okay, hose kinked, you're meeting resistance. It's harder for that water to flow through it, And then the voltage would be the faucet. How much water do you turn it on? Do you turn on just a little so there's a little bit of a trickle, or do you turn it on full blast so you have a whole bunch of water, or you have a whole bunch of pressure pushing that water through? So how much water turned on? All right, so just a little bit of an analogy for you to be able to tell the difference between the current, the resistance, and the voltage. The other two things that we're going to be using are things that you have used before, power and work. Power, capital P, it's the rate at which electrical work or electrical energy is done. It is always measured in watts. Whenever you use the equation for power, it comes out in watts, which is abbreviated with a W. That can't get confused with work. Electrical work is the same variable as it was before. Now we're just dealing with electricity, but it's still work. So it's still a W, okay? Watts is the unit that we measure power with, whereas when you see it in an equation, it stands for work. It's the energy needed to move electrical charges. We got to get those charges to move. You need electrical work in order for that to happen. Two different units that it can be measured in. Electric companies measure it in a kilowatt hour, kWh, or what we're used to measuring work in energy, we're both measured in joules. Okay, so we're going to have to be able to convert between the two of those because both units are going to be used. All right, so these are the basic things that you're going to need to know: which variable it is, its definition, the unit it's measured in, and then how to abbreviate that unit. Moving on, the voltage or the potential difference across the outlets in your home. When you plug things in, you are getting 120 volts. That is a given. So anytime you have something that's plugged in, you're going to assume that the voltage is 120. Straightener, hair dryer, microwave, anything like that, if you plug it in, you're going to assume that the voltage is 120. The rest of the world doesn't run on 120, it runs on 240. If you've ever traveled out of the country, you usually need an adapter of some sort. That's if you're plugging in your hair dryer. If your hair dryer is made for 120 volts and you plug it into 240, it can blow the circuits or it can fry your hair dryer. Okay, so you need to plug it into an adapter, which then gets it ready to it slows down that voltage before it gets to your hair dryer so it doesn't overload the circuitry. Okay, the reason for this is really the age of the buildings where they were made. So the United States was first starting to put electricity into homes in kind of the 1910s, 1920s. The only type of electricity at that time that was safe was 120 volts. Okay, by like 1920 something, 50% of the houses had electricity. Over in Europe, the houses had been around longer. It took them longer to get electricity into people's homes by about 20 years or so. By that time, they had found a way to make electricity a little more safe, so they were able to put more voltage into people's homes, and that's kind of the reason why the different voltages are what they are. It was just when houses were starting to get equipped with electrical outlets and electricity, the type of electricity that was safe. Earlier, less electricity was safe. All right, our first equation for electricity, Ohm's law, delta V equals I times R. The voltage is equal to the current flowing through it multiplied by the resistance. So how much is going multiplied by how it gets slowed down is equal to the voltage. All right, for an example, the resistance of a curling iron is 19 ohms. All right, my R is 19 ohms. What is the current? So my unknown, I need to solve for current. The equation, delta V equals I times R. I have R, I need I, which means I must know delta V. You're going to assume anything you plug in is going to be equal to 120 volts. So delta V is going to be a given 120. So as I plug it in, I'm going to have 120 equals I times r was 19. All I have to do is divide over. It's a nice easy equation, and when I do, I find that I is a little over 6. I found it to be 6.32, and then the unit of current is amps, or an A. All right, moving on, our second set of equations are going to have to do with power. So in the scheme of things, the equation for power is the same whether we were expending horsepower moving something a distance or when we're talking about electricity. Okay, it is always measured in watts. All right, so anytime you use an equation, the power that goes into the equation or comes out, you have to have it in watts. It is the rate at which work is done. So if you go back to kind of your forces, work, power, energy area of your equation sheet, what you're going to find from earlier is the power is equal to work over time. We are still going to use that equation right there. We're going to use it a lot. In fact, it's going to help us solve for the cost of electricity. If you use your PlayStation 4 hours a day, how much does that cost you? We're going to be able to use that equation to figure it out. We are also going to have a second equation for power that will help us specifically when we're dealing with current and voltage. And it is power equals I delta V. So you can find electrical power specifically if you know the current and you multiply it by the voltage. Both equations work. We will use both of them at different times throughout this unit. All right, example number 2. An electric space heater is connected across a 120 volt outlet. So I told you this time it was 120, but I didn't have to. You assume a space heater, if you're heating something up, you have to plug it in. So delta V equals 120. The heater uses 1500 watts of power. So my power is 1500 watts. Calculate the resistance. So my unknown is going to be the resistance. Okay, I only have, if I look at my 3 equations, that one, and that one, I only have one equation that has resistance in it. So I am going to have to use the equation delta V equals I times R. In order to solve for R, I need delta V, which I have, and I need current, which I don't have. So this is going to be a 2-step problem. I am going to have to first use what I have, power and voltage, to solve for current. So I'm going to have to use power equals I delta V. And then once I solve for my current, I'll be ready to solve for my resistance. All right, so here we go. Starting with the first equation, my power was 1500 watts. Have to be in watts, we're good to go. Well, I don't have I, but I have delta V, which is 120. I need to divide the 120 over, and when I do that, I get 12.5 for my current. I equals 12.5 amps. Once I know current, I'm ready to plug it in right there, and I also know the voltage, it's still 120. So I will have 120 equals 12.5 times the resistance. Once again, all I have to do is divide over. If I take 120 divided by 12.5, I find my resistance is about 9.6 ohms. And that is my final answer. So 2-step problem using 2 different equations in order to find resistance. You're going to do that in lab this week a couple of times. Finally, last piece, converting between joules and kilowatt hours. So if you look up here, a quick reminder, kilowatt hours and joules, they are both units of energy, or of electrical work. Okay, so they're both units of work. We have to be able to go between one and the other. Think of like meters and feet. We have to be able to, in hours and seconds. We have to be able to convert between one unit to another. All right, so that's what we're gonna do. If you rearrange the power equation, this one right here, power equals work over time. If you move the time over by multiplying it to get work alone, what you end up having is work is equal to power times time. Okay, work is measured in joules, power is measured in watts, and time is measured in seconds. So if this equation holds true, then a joule has to be the same thing as a watt times a second. Box that in, circle it, do something, star it so that you can find it later. A joule is the same thing as a watt second. All right, that's going to help us. If we want to convert from joules to kilowatt hours, I have no idea how to do that because a joule doesn't really tell me much about a kilowatt hour. Okay, but instead of thinking of it as a joule, if I think of it as a watt second, then watts and kilowatts, I can do that. And seconds and hours, I can convert that. I have a two-step conversion. All right, so example 3, convert 50,000 watt seconds, or joules, watt. Notice it's times a second, not divided by, so they're both on the top. I want to convert that to kilowatt hours. I am going to need 2 steps in order to get from one to the other. All right, it doesn't matter which one you start with. You can start with watts to kilowatts or seconds to hours. I just always start with what comes first. So I need to change watts into kilowatts. Watts are on the top, which means they have to go on the bottom. If you can't remember that kilo means 1,000, this is on your equation sheet. There are 1,000 watts in a kilowatt. I have canceled out watts and I have a kilowatt second, but I want a kilowatt hour. So my last step, I need to change seconds into hours. Seconds are on the top, so they have to go on the bottom to cancel out. In 1 hour, there is 3,600 seconds. All right, so 2-step conversion. I need to take my 50,000, I need to divide it by 1,000, that gets me down to 50. And then I need to keep going, and this is also on the bottom, so I also need to divide by 3,600. When I do that, I get sorry, I don't know how to close these things. 0.014, and I am now in a kilowatt times an hour, kWh. And you can put it here too if you prefer. All right, so that is it for the notes. For the problems, you will work your way through different examples, kind of like these right here, using your equations, doing some conversions. Those need to be submitted by Wednesday night before you go to bed, along with this quarter 4 info. Okay, from here, I'm going to pause and I'm going to get my lab set up as well. When you're ready for it, you'll just skip to this part of the video again. You'll look for my lights that are all lit up in the back, and then that's how you'll get the data. Or you can put in the data right now for the electricity lab and crossword puzzle, and you can just write it in now and get to it later. That won't be due until Sunday. But you can always turn it in early. I would love that. It helps me out getting some grading done early. All right, so I'm going to pause, set up the lab. Here we go. All right, here we go. I have my lab all set up. Hopefully you can see everything okay. The plasma ball, it has to be kind of dark in order to see it really well because it's kind of like a faint pink color. All right, so across the top of the lab is a brief review of all the different variables and the units and stuff that we got in the notes earlier this week. Okay, from there, Kahoot. You are going to go to Kahoot and you are going to play. You can play with somebody else if you want. You can make a sibling play with you or a friend. Or if you have 2 devices like your iPad and your phone, one of them starts it and then you can play it on the other. You're going to put your score in. If you're on Zoom with me, we'll just do it on Zoom. All right, station number 1 is the plasma ball. That is this guy right here. So hopefully you can see this faint pink color. It's got electricity kind of all throughout it. And then when you go to touch it, it puts all that electricity in the one spot. Wherever you touch it, it flows the electricity to that one place. Very cool. I got it on Amazon for like $10 if you're looking for one. All right, the two things that you have to know, the current of the ball, this plasma ball, it is 300, so put that in, 300, and notice this is MA, that is a milliamp, milliamp. When you need that, I have it on your lab for you, that means it's 1,000 milliamps in an amp. Milli means 1/1000, so it's 1,000 times smaller. There are 1,000 milliamps in an amp, so 300 MA. And then the power coming from the adapter, it's just a USB adapter, plugging in right here, the power that it pushes through is 1.5 watts. So 1.5 watts. All right, the second station, as you work your way through the math of it, and then when you get to, I guess, 1C, it says once you have an answer, check the ball where it plugs in to see if you were right. You should get 5 volts is what the adapter is actually pushing through. So even though it's plugged in at 120, it has an adapter that pushes it down to only 5 volts going into it. So that's how you can check your work for 1C. Okay, station number 2 is the lava lamp. Okay, this baby, if it's not too hot, it has a light bulb underneath it. The light bulb is 25 watts. 25 watts, and it is plugged in, so the voltage is 120 volts. So 25 watts and 120 volts. You will be able to use that in order to calculate the resistance of the lamp. It takes energy in order to push it through the light bulb filament, so that provides resistance. That's what you're solving for. And then you're going to use the last two, you're going to have some conversions looking at that kilowatt hours and your watt seconds. So, all right, those are the 2 things we're going to be playing with in lab today, or this week. Don't forget, 2 assignments due for Wednesday, and then the other 2 will be Sunday. Everything's labeled in Schoology, but text or email me with any questions. Thank you.